So good morning, everyone. Let's start with a question. What is a tree to a mathematician? It depends on the branch of mathematics you work in. Branch name is not a coincidence. Probably the first idea is a tree in graph theory, so-called combinatorial tree. It is a connected graph without circuits. Formally, a pair consisting of the set of vertices and the set of edges. I think that the notation, the picture is clear. I would like to mention that for any two vertices, there exists a unique path without backtracking, joining them, and the length of this unique path determines an integer valued metric on the set of vertices of this tree. When drawing a tree, we usually join vertices by segments, arcs, and thus we come to the notion of the geometric realization of a combinatorial tree. It is a metric space. Its underlying set is formally the disjoint union of a family of isometric copies of the real unit interval, one copy for each edge, with an appropriate identification of endpoints. And the metric is naturally defined to be the length of the shortest path. It is illustrated for points x and y here. Thus, we get a metric space, and it has values in the real numbers, not only integers. This can be generalized to the concept of so-called real tree or R tree. To start with, a segment joining 2 points in a metric space is the image of an isometric embedding of a suitable real interval into X. It is also called a geodesic segment. And we define an R tree as a metric space such that any 2 points can be joined by a unique segment. If we have 2 segments with a common endpoint X, their intersection is also a segment with X as one endpoint. And in particular, if the intersection is a singleton, then the union of the segments is also a segment joining Y and Z here. So these 3 conditions reflect the tree-like structure of this metric space. Of course, there are equivalent characterizations of R trees. For example, they are precisely connected zero hyperbolic in the sense of Gromov metric spaces, or uniquely arcwise connected geodesic metric spaces. Let me give an example illustrating these conditions, and it is also an example of a real tree that is not the realization of any combinatorial tree. It is even not homeomorphic to any such realization. Here we have the plane, and the metric is so-called Jungle River metric. I think it is clear. We teach it to students. The x-axis is our river, and we have 4 points marked, and one can check that the 3 defining conditions are satisfied. The notion of a real tree can be further generalized to lambda tree. It was done by Morgan and Shallen in 1980s. And to define lambda tree, I will have to introduce briefly lambda metric spaces. So let lambda be a non-trivial, totally ordered abelian group. The examples are subgroups of the additive group of real numbers. These are so-called Archimedean groups. And there are also non-Archimedean. For example, the direct sum of 2 copies of Z with the lexicographic order, or hyperreal numbers. We can define a lambda metric on a set X as we define a usual metric, except that we allow the metric to take values in lambda instead of R. The conditions are natural, triangle inequality, etc. And as we would like, the family of open balls is a base of a normal Hausdorff topology. The notion of isometry is meaningful. The group lambda itself is a lambda metric space, and we can define an interval in lambda as usual in this ordered structure, the elements between A and B. Having this, we can generalize R tree to lambda tree. The defining 3 conditions remain the same. They reflect tree-like structure. The only differences are that it is a lambda metric space, and we have to understand that the segment here is the image of an isometric embedding of an interval in lambda. I make an important remark. Under this definition, Z-trees correspond exactly to combinatorial trees, more precisely to their sets of vertices with shortest path metric. Let's go to the theory of isometries of lambda trees. There are 3 types of isometries. An isometry G is called elliptic if it has a fixed point in X. It is an inversion if it has no fixed point, but G squared does. For Z-trees, combinatorial trees, it means that G reverses the vertices of one edge. It stabilizes an edge, but change places of vertices, swap them. And the remaining isometries are called hyperbolic isometries. It is known that if lambda is 2 divisible, for example, the group of real numbers, there are no inversions. And now I can define the key concept of my talk, the translation length. If we have an isometry G of a lambda tree, its translation length is defined to be 0 if G is an inversion, and otherwise it is the minimum of the set of distances between X and G of X over X in X capital. It can be shown that this minimum is in fact achieved. And the axis of a hyperbolic isometry G is the set of points in our lambda tree for which this minimum is achieved. It is a non-empty subtree, isometric to a convex subset of lambda. Convex means that if A and B belong to the set, the intermediate points also. And under this isometric identification, the action of G on its axis corresponds to the translation by the element norm of G of lambda. And this justifies the terminology, translation length. Let me give two examples. The first is the Cayley graph of the free group of rank 2. It is treated as a Z-tree. I have marked in blue the translation, the axis of AB. It is, of course, infinite. I marked only a finite amount of points. The vertices in blue are moved by AB according to the arrows by 2. The translation length equals 2. And the axis is isometric to the integers, to the Z-tree Z. The second example is Briat's tree. If we have a field with a non-Archimedean valuation, there exists a lambda tree X and an isometric action of GL2 on X with translation length depending only on determinant and trace of G. The action of the special linear subgroup is without inversions, and if the valuation is discrete, for example, p-adic valuation, the tree is an infinite regular combinatorial tree. There is a beautiful book of Jean-Pierre Serre, trees, and the whole second chapter is devoted to the action of SL2 over a local field on its Briat's tree. Kahler and Morgan in 1980s asked how the translation length can be axiomatically characterized. They defined the notion of a pseudo-length. A pseudo-length on a group is a function from G to the non-negative elements of our group lambda, satisfying 4 conditions. The first condition is technical. It is meaningful for groups which are not 2 divisible. The second is invariance under conjugation. And the alternatives 3 and 4 may seem technical, but indeed they are very, very powerful for proving things. Walton Perry in 1988 proved that a function is a pseudo-length if and only if there exists a lambda tree and an action of G on X by isometries such that the value of pseudo-length is the translation length of G. So we can talk equivalently pseudo-length and translation length function. It is the same. I introduce the notion of a ping-pong pair. We call 2 hyperbolic isometries a ping-pong pair if they satisfy the algebraic inequality in the language of pseudo-lengths. Or geometrically, it means that the intersection of the axes of G and H is empty, or it is a a segment shorter than a minimum of translation length, as in that picture. Here we have recalled the notion of a properly discontinuous action of a group G on a topological space. It is clear for uh, algebraic topologists. They are precisely actions of covering space actions. And Kahler and Morgan for R trees and Ian Chiswell in general for general lambda proved that if J acts on a lambda tree by isometries and AB is a ping-pong pair, then the subgroup generated by A and B is free of rank 2 and acts on X properly discontinuously and without inversions. The proofs are geometrical. They refer to the geometry of lambda trees. There is much drawing of diagrams, pictures in the proofs, and they make use of ping-pong lemma to show the freeness of the group. I have chosen a different approach, a combinatorial one, and I obtained an explicit formula for translation length. So if we have a pseudo length on G and AB is a ping-pong pair, then we can compute the value, the exact value of pseudo length of W for any cyclically reduced world W. It depends on pseudo length of products of consecutive generators. In fact, it can be computed for all words since pseudo length is invariant under conjugation. My proof methods are only combinatorial and use and rely solely on the axioms of pseudo length, not drawing any pictures. And it can be my formula can be written in another form if W is written as a product of syllables of powers. Then we have expanded formula. We can draw the corollary from it. It is exactly theorem of Kahler, Morgan, and Chiswell. So if we have a ping-pong pair, then the group they generate is free of rank 2, acts properly discontinuously and without inversions on the corresponding lambda tree. It follows from the fact that the pseudo-length of W is separated from above from 0. At least one element does not vanish, and it is greater or equal than minimum of pseudo lengths of AB, AB, AB inverse, which is positive in lambda because of the ping-pong assumption.
Yes, Camille, I sorry for interrupt you. Time is out. Maybe you can just say a few minutes, 2-3 minutes.
Very shortly, I also investigated inverse problem and I constructed a pseudo length given some conditions. The corollary is that under some conditions there exists a unique pseudo length with prescribed values on AB, AB, and AB inverse. And the application is a characterization of purely hyperbolic pseudo lengths on the free group of rank 2. It is not my theorem, but uh, the pseudo length, any purely hyperbolic pseudo length on the free group depends on four scalars from lambda and an automorphism of the free group, and that there is an algorithm. It was due to Mark Kalar, Karen Voigtman, and Ian Chiswell, but I provided a concise form. This argument was geometric. There was geometrical some parts and uh, not combinatorial. I gave combinatorial uh, approach. There is a short list of references, general works, and my preprint translation length formula. Uh, so that this is all. Thank you for your attention.
Yes, thank you very much. Thank you.